we're live. Building Wanix from scratch. Day 4, I think.
Sounds right.
Yeah.
Like more than that, but I guess I've been working streams. And we've got Rohit, shadowing, and Tara here. Both of you should have headphones.
Yeah.
Yep.
Okay, cool. Well, let's get into it. Some exciting stuff. I guess maybe I should say we're working with Wanix. It's a development environment made a year ago, and now we're sort of building it over from scratch. I don't know, I'm sure, Rohit, you've been picking stuff up, but I'm sure it's not as interesting because we haven't really made it do anything interesting, right? So
I mean, yeah, that is true, but it's kind of interesting seeing basically like the bare bone, like skeleton of the system.
yeah, how it's sort of
So
coming
that,
together.
yeah, how it's sort of coming together, and it feels like it's gonna help me a lot once we are building stuff later.
Yeah.
Because I know the system more now, then it will be easier for me later to build on it, kind of.
Well,
So it has been helpful.
that's good to hear. Luckily, I think today will be a little bit more interesting because I ended up doing a bunch of work stream since the last stream, and instead of going over it all, it's actually to a point where I can sort of demonstrate what we can do. So kind of the initial goal here, there's sort of this phase of building up this infrastructure for doing file systems. And after this phase, I don't know. Yeah, once we get this stuff done, we're kind of going to change modes and then try and get it all working in the web and working with WebAssembly and TinyGo and stuff like that. That'll be interesting, but for now, our goal is trying to get this core idea of if everything's a file system, and we'll call a file system a device, we can create those devices through the file system goal, that we could create an in-memory file system and then mount it and be able to read and write data to it, and have done all of that through the file system in this Plan 9 style way where we can allocate a sort of resource with a shell command like this, where we're just reading using cat to output, read this new memfs, which gives us an ID to a directory that's created under dev, this, and then we have sort of control over this resource through a file system. One of those sort of ways to control it or send commands is through a control file, and then we'd have type as an example of data we can expose about around it, and then when we mount it, we can put the mount here. So after allocating, we would just kind of echo mount. It's like running the mount command in the control file, which shell like this. And then we'll have a mount. And then the idea is we can put that mount somewhere using a bind command. So instead of accessing this just through this path, we'd be able to put it at /data or wherever we want through this kind of global control file that lets us do commands like bind and unbind. Once we've done that, we would have, in this case, an in-memory file system running at data, but we made that through a file system. And we're pretty much there. I can show you now that think anything's terribly new. Let's see. This is from, well, so before, when we ran Wanix serve, we would run a in-memory file system and then mount that with Fuse at temp Wanix.
Yeah.
Now we actually have this sort of, hard to say because it's a file system device, but a device is a file system. So you can call it a file system. But basically, this, which I guess I've started putting this stuff in the kernel, and if I updated reflect that kind of stuff around. So I don't know if we started looking at this yet, but basically here is defining a file system that lets us control file systems, what I was showing. It's a struct that's basically holding a map of the resources that we create. And even if they are other things, we can store them as a file system, since ultimately we're exposing them as a file system. And then the types of file systems that we can create, what would be listed under new, are registered here. So we can all register. And then other than that, this device just implements the file system interface and our extension, the open context one, come back to. And yeah, you can see that there's a couple of cool utilities that we've made in FSKit to kind of assemble this file system out of other pieces. So for example, right now mapfs basically lets us define a map where every key is a path, and then the value is another file system. We have this FSKit openfunc, which lets us define a file system with a closure that just defines the same interface as open context. So here we're saying this file system has a file called new. It's actually a directory. So when we open dot, which is the root of this file system we're making, which is also the new file, that's a directory. So we assemble entries of file representations from our types, and then we have this helper that lets us make a dir file, give it a name, its file mode, and then all the entries, and then we get a listing of what's in new. And then otherwise, any other file in this sort of sub file system under new is going to be what happens when we open one of these, what happens when we actually want to allocate one of those file systems. And I made another sort of helper here called a func file. So this is a file that uses our node builder, but then also lets us define some functions. So here's a function that's called the first time the file is read. And so that's actually where we are going to create or sort of allocate the resource. So based on the name of the file, we look up our types, we get the factory, increment our ID, we convert the ID to a string, put that in resources, declaring a new resource. And then we're passed in the node that we're being read. And this is before the read has happened. So we can quickly set the data that will be read, which will be the resource ID. And then if we go back up here to what this device has, besides this map, which might have other things, we have a union FS, which basically is going to combine this map FS with any other file system. And so here we use mapfs again, but just to sort of type assert resources, and resources is this map of IDs to file systems. So it's basically putting those together. As we add stuff to resources, it will make basically directories in here. And then pretty similar, a resource. Once that's created, in that we have a little sub-file system here. Sort of set up the same way with mapfs. We've got a control file. And this is kind of cool. This is another helper like the func file, except it lets us define a command in pretty much the same way we define this command for our command line tool. Just because it sort of adjusts the semantics to being about running a command, because that's basically what a control file is for. We send commands into it. So what this does, and we won't get into it unless we need to, but basically when this wraps a version of func file, except on read, we have an on close, so we can write data to the file, and then on close, it sort of commits it, and it will parse what was written, and then split up the args, basically split by space, and then pass them into this command. And basically in here, we're just saying, hey, if arg0 is mount, then we're gonna do the mount, which basically is call the factory that was associated with this allocated resource, set the file system based on what was returned. And then once file system is set, then there will be another directory in here called mount that is basically that directory. And then there's also another little helper here, field file. So for the case where we just want a file that gives us a value, field file lets us just specify a value here. It's the resource type. It's TYP because E would be a keyword. I don't love it, but I can't think of a better way. Sometimes people will do underscore, but
Yeah.
we're already abbreviating and shortening things. Optionally, we in this field file we can set a setter. So this is what happens when we write to this file. It's basically going to trigger the setter with the bytes that were written. So we basically have built up these little utilities to build up little composable file systems. And so now the result of this, let's actually Wanix serve. So this is gonna errors, but not fatal errors, but the output. So that mounted it into temp Wanix. Here, look into it. I'm actually doing all of this without changing into the directory, because when you're working with Fuse file systems, if you have a shell that's in a directory, when you close it, it will basically get stuck. So I'm just kind of sitting outside of the directory and doing all these commands from outside. But anyway, ls Wanix, there's control and new. Maybe we'll see a little bit more. It's nope. Maybe I'm thinking of lists them vertically. Anyway, if we look in new, we can see hello fs. That was the file system we registered here. It's hello fs. And this is the constructor. So basically it's going to create a mapfs with a hello file and a hello world. So let's see what happens. Again, the goal, let's look kind of like this. We can do a cat, which, since Rohit, you're not super familiar with like basic Unix commands, right?
I know
I mean,
Yeah,
ls,
I'm
cd,
like
and
this.
stuff, but I think once you get into cat, that's more like you're working. Cat's short for concatenate, and it
Okay.
basically was originally designed to um, basically list a bunch of file names, and it'll just
Mm-hmm.
output those files together. So it's concatenating them into one stream. But
Okay.
in the Unix sort of philosophy is, um, use what you have.
Mm-hmm.
And so
Mm-hmm.
I am a little bothered as a designer that cat is called cat, even though it's mostly used to read files and
Mm-hmm.
output them. Um,
Mm-hmm.
so it's just one of those things you just learn as you go. And part of that is because Unix was made by people that were making it for themselves. They weren't necessarily making it to be used by a mass audience, especially in the beginning. And so they were being very pragmatic. Also, in terms of resources, like early video games, they were constantly trying to maximize utilization of what they had. Anyway, cat. This is how we output stuff. So if we were to cat new MFS, oh, sorry, it was called HelloFS.
Hello, yeah.
All right, we got a 1. And if we look in Wanix, there's now a 1 directory. We can cat Wanix. The idea is, as you see up here, this runs a subshell, and this sets a variable. So a common thing you might do is output, this resource ID and put it in a variable, and then you can use it in paths like this. We're doing it by hand. But anyway, this is sort of how they did stuff. So Wanix 1 CT. Oops. Type just C. Hello. S. We don't have mount because that's sort of a separate step. I think with these file systems, because you don't have the option to really specify any parameters when you're allocating something this way, in this pattern. By the way, if this was really Plan 9, it would have looked like cat. Instead of new, it would be called clone, and you wouldn't be able to specify a type. And so maybe I'd do that through the control file or something. But here, as an experiment in this design for Wanix, we're starting from scratch. I figure, well, maybe we want to specify the type. So, we basically have the option to add a directory path to this. So maybe we can use that to specify the type. So that's a little different from Plan 9. But otherwise, if we had any other parameters, maybe this was a file system that connected to a remote machine. How do we give it the address to connect to? So we would do that when we pass something. We basically have a command that we send to the resources control file. In this case, we don't have to set any parameters. I think we do output args then. So if we were to do something like this, we'll echo. And echo is another one of those things where it's a command that will literally take the arguments and then output them. And so this is commonly used to basically write data, because everything's just piping streams around. So the output of this is a stream that we can redirect if we wanted into a file. We could put it into temp file, and then if we cat temp file, there's hello world. So again, very kind of Unixy stuff. So let's echo mount, and I'll just make up some arguments, and we'll pipe it into, as if we're writing a new file. but we'll, oops, actually. All right, nothing happened as far as we know. But if we ls Wanix1, there's now a mount directory. Look in mount. Get a hello file, which is what we only started with that we would have in this HelloFS. It looks like we also printed out some stuff. If we go back here, the sites of the logs from Fuse and some extra debugging for some errors that aren't actually errors because file does not exist is not really a fatal error. It's just how we know that a file doesn't exist. Somewhere up here. On a file not exist. And then LFS. Well, for all the operations that we did a command and we got getting closer. There we go. There's our mount command. So that's when we piped or echoed mount ABC into the control file. And then it allocated our file system. So it ran this. Args eventually passed in here. So these arguments, we could use in some file system that connects to remote system or whatever to configure that. Anyway, then our hello file, which is just I renamed some of the stuff. So now instead of node, it's raw node. So here's some bytes. So hello world. So we should see in this file, hello world. Curious if we can write. I think I ran it. Blocking for some reason.
Do we have to specify that it's a writable file?
So that's a good question, and it's complicated because one of the tricky things about the abstractions that we made here, make file system, all this fskit stuff, mapfs, fs, openfunc, all of these things are in a way wrapping values. And every time you wrap a value, you lose some of the capability. So, example. So got an fskit. When you create a node, if you open a node, you get a node file. And that implements the file interface. Close, stat, read. That sounds familiar, right? It also implements some other optional stuff. So seek, being able to change the cursor in the file. Read at, which is a helper that basically lets you do that in one operation. You can go to an offset and then do the and then there's write and write at. So this type node file implements all of these interfaces. But the problem is, for example, we're doing one of the problems we had in the last stream had to do with kind of setting the name, because I kind of wish I still had stuff, but we had like this idea of a file system is, it's basically a directory of files, but a file system also has its own root identified with period, which is similar to the idea of the current directory normally. If we make something like a mapfs and we want to mount this file system at mount, so we would be able to go to mount, and then we'd be able to go to. The problem is, from the perspective of this file system, what mount is actually a file called dot. So we had to come up with a way that when you're mounting a file system like this under another file system, that it kind of carries the name of the point where it was mounted at. So that if you were to look at this file, it would say my file name is mount. Does that make sense? That's kind of the problem.
Yeah. Yeah.
And maybe there's a design way, like, I don't know. I'm for the most part, I'm dealing with a lot of trade-offs, and it feels like we kind of have to live with something like this. We just have to somehow deal with the problem. And I think in the last stream we were playing around with some stuff, and I eventually got it to work by creating this namedFS utility, which basically we can call namedFS, give it a file system and a name, stores that name, and then it implements the file system interface. And normally it will just call open, it'll pass it to the file system that we're wrapping. But if we're opening a file called dot, we'll actually go in and get the rest of the file information. We'll open dot on the wrapped file system. If it's a directory, we'll return a file, a struct that implements file called renamed_dir, or if it's a file, we do file. The reason we have to do this check kind of comes back to what the point is. Renamed_dir is then wrapping an FS file, because in theory this should work for any file, not just concrete types like our node or whatever. And so, and specifically this is for a directory, so I guess I should say, because we're not naming this thing like this is called embedding a value inside a struct. And when you do that, it's sort of like inheritance. You're familiar with inheritance, like kind of basic object-oriented?
Yeah.
It's kind of like inheritance, where this value will, any methods or fields that it has, will be available on this one. They're just sort of passed through, unless we implement our own on this type. So, for example, we customize type, or stat here, because stat is how we get the name of a file. So we call stat on our file that we're wrapping, but then we return a raw node based on that file information, but with our custom name, hence naming it. So now whatever file this wraps, when we call stat, it's gonna have this name. So that's kind of the general idea of how we're doing this naming thing. And then the problem is, file is an interface that only implements 3 methods. The idea is that, if you implemented write and stuff like that, we could do a type assertion on this value to say, hey, do you implement this interface? Give me an object that implements that interface if you do. It won't work on this wrapped value because there's too many layers of indirection. Go is just like, okay, this file doesn't have write on it. It doesn't, so we can't sort of type assert this wrapped type for any interfaces for the underlying type of file. I might be explaining this kind of confusing, but does that kind of follow what I'm saying?
I mean, yeah, I kind of get it. What's happening?
Yeah, it's like basically, because we're wrapping stuff, because we're nesting stuff, the rules of Go's sort of like, pass through for interfaces don't quite work well. I could show an example. I just didn't want to spend too much time on this. So basically, any interface that could possibly be implemented by file that we would want to use here, we have to re-implement here. So for example, in the case of a directory, normally you would type assert very much like this. If a file is a directory, you could type assert read dir file, which is an interface that basically is file but has read dir, which gives you directory entries, read directory. So we have to do that directly on the file and actually implement a method here. That's the only way we can make sure that this is type assertable for read dir file. Which means, for example, file, we have so many more things. We have to implement all these other interfaces. Luckily, we've got all these helpers for them, so it feels like boilerplate, but luckily it's pretty minimal boilerplate because we can just pass it off to these helpers that we made in the FS package, which, if you don't remember, most of these are doing things like this, checking to see, does this file implement reader at? If so, call it. But if it doesn't, potentially do something else. For example, reader at is basically the interface that uses for read. Normally you would expect read is usually just give me some bytes, and it'll use the internal files offset or cursor to figure out where is it going to start reading those bytes, basically at the point where your last read finished. In use, it always has this offset, which means we would need to do at, but not all files will implement read at. But because we have this helper, we can basically do fallback. So it doesn't have reader at, but we can create the same functionality if it has a seeker, which means does it implement seek? If it implements seek, then let's now seek. That's basically moving the offset. And then once we do the seek, we can do a regular read. If it doesn't have seeker, we can even do another fallback, which is if we're always reading from the beginning of the file, we'll just read up to that offset and discard the data that we read, and then we can do a read. So these helper utilities are really pretty handy. And then it turned out that they also made making the wrappers really nice, because we have to re-implement these functions for type assertions to work if we're wrapping all of these files. So anyway, that's how we solved that problem. I already, the whole nesting thing. And we'll see how it goes. But that this blocking on write, if we come back to where we originally came in, because there's so many layers of wrapping, and there's first, basically, if we were to go through this, it would, kind of start with fuse. This is a write. So actually, if we look at the logs, it doesn't even get to write. It does a lookup. The fuse thing that it does before most operations. Does a lookup. This might actually be it. So that's fine. Obviously, it's just looking up some metadata for file. And then it does a sub. We didn't really look at this before, but take me to the sub is utility in the official IOFS that the idea is give me a file system that represents a sub path of this file system. It's kind of like, it's almost like there's two concepts of directories here. Like, in a way, a file system is a directory, but then also we have the idea of a directory file. But anyway, because we're modeling directories always as file system, this idea of sort of drilling into a file system to get a file system that represents a subtree of it. That's what this is for. Unfortunately, we look at the implementation for this, which highly recommend reading. Go standard library code. It's doing stuff kind of similar to what we've been doing. First validates the path. If the directory is the root, then we're not really having to do anything. We'll just pass through a file system. Then we do a type assertion. Does this file system implement its own sub method? If it does, we'll call that. Otherwise, we'll basically wrap it in subfs here. And so subfs is defined here. It's almost like our rename stuff. It has some helpers for sort of like going from the short name to the, the relative names. And then it looks like it implements open, which is the file system interface. It implements a bunch of other things that are kind of optional, that are just kind of convenience things, like directly implementing reader, file, and glob, and then also sub, which looks like it's more or less doing the same thing as the utility function. But the file, so this is an example of, let's say we started this memfs file system, which, by the way, I cleaned up, and it uses all of the fskit helper stuff. So now this source file is literally just, the methods, open for the file system, and then all of the other extra sort of mutable methods like create, makedir, mod, right? You were here for these.
Yeah.
I'll have some of that, but the problem is even though we implement all of these methods, when it's wrapped in subfs, now it doesn't have those methods, right? It has these methods. And so this is what I meant in that you can't, when you wrap stuff, you then can't type assert for getting the extra methods. So we'll probably have to implement our own subfs that does something very similar to this, where we basically implement all of these, create, etc., and hopefully have some kind of helper to make it so that we don't have to just re-implement. But I guess my feeling is that open I guess my feeling, and I might be actually wrong about this, was that the problem with using sub is that it will only return read-only files because something's going to get wrapped in a way where now it doesn't have write. And so then it gets confused because later on when we try and write, it's not going to be there. But normally we would get an error because it'll be like, oh, you don't have write, and so it'll return an error. But what's happening here is this blocking. Anyway, the short of it is, I don't know why it's happening, but at least at the moment, we'll kind of ignore it and come back to it. I'll make it. Did forget. Right, blocking. LFS. Cool. And I think actually part of it is because maybe this is where we get to the meat of it. MapFS is read-only. These utilities, map and unionfs, they're made for read-only file systems. Otherwise, we'd have to implement all of the, make dir delete on all of them. So at least for now, we are only using them to virtual file system, basically. So, let's get started with some stuff. Now that we have a file system, the thing is we can't do bind. So we've mounted the file system, but the reason why we can't do bind is because this functionality of binding, of like rewriting, creating kind of a virtual path that redirects to another path in a way. That functionality doesn't exist so far in our system. We'd have to create, a control command for it, but then how would it actually implement that? A while ago, I implemented this namespace fs, and this was basically the prototype for implementing Plan 9 style bindings. So like some of our other file systems, we implement, in fact, we can get rid of some of this because this is the stuff that we could, the kind of cruft we'd have to create for every file system. Now that we have fskit, we can get rid of a lot of stuff. And so we'll have to basically change. Oh, what was file info was just yeah, it was just something that implemented. Yeah, we don't need that because we same with this directory. to a type. One of the patterns in Go is usually you don't, when you're returning a struct value that implements an interface, you usually don't want to return the interface unless this is part of an interface, because the whole point is you don't know the specific types that you're using. But normally you want to return the specific type, in this case fskit. Because this is type assertable. I forget the specifics, but kind of the rule of thumb is you would return you typically prefer returning concrete types in your outputs, and your inputs, your arguments. If you can, you prefer interfaces. But I can't back that up. And then here we're going to entry file name, mode, no bytes involved here. We don't, I guess we can actually pass fi, because that will basically copy all the stuff. In fact, let's do this on Node, which is the version of this that takes arbitrary attributes. They're kind of in order, so we'll first pass fi, and then let's see. What else do we fix? Var file. See if autocomplete can do this. I think that's right. Yeah. See how much simpler the code gets when we create good helpers? That's kind of a big part of programming it. I mean, if you're good, it's building these little primitives that make it easier to build more complex systems. I don't know if you've gotten an opportunity to do that much yet.
Like creating helpers, or like
Yeah, I mean, I guess it's not uncommon to create helpers, but to me, creating helpers is slightly different than creating your own abstractions. Like, it's easy to create a helper that's like, oh, I just want to reuse this code. I'll take whatever this functionality is and wrap it in a function, and then I can call it multiple places. But to actually change sort of the semantics and the simplicity of it, that takes some deeper thought. That's kind of what creating abstractions is about. Now for whenever I want tab to autocomplete, it doesn't do it. I have to actually read what's going on here. Basically, we're adding entries. I don't think we have a mechanism with Node. We'll have to a separate thing to track. So, I'm not really explaining this code because I'm doing it a bit. I'm just trying to refactor this stuff to use our fskit. Yes. Yeah, entry info. Raw node based on entry. And we don't need to specify. Sorting. let's, come on, autocomplete. Does that look right? I keep going back. Okay, name and again, there might be some code in here that could be let's see. File info is now and it's trying to autocomplete this. It's pretty close. Your file takes a node that represents the actual directory file and then the entry for it. Oh, it wants directory entries, even though our fskit node implements directory entry. It needs it to I don't know, be declared in that time. Basically, I think what we need instead of fskit entry. So we're declaring this variable with this generic interface type, but we can still assign everything. Still assign nodes to base. Then when we get down to this, it's supposed to work. What is this? Oh. That. What's going on? So that's all good. Info. Well, let's see how list is used. Very similar. It's going to be used to create a dir files. Maybe this. This is all very similar. I'm basically copying the same code over and over. This is the code that synthesizes parent directories. But it looks like we... Right. And then lastly, we need to create a directory file, which that okay, list, it needs to be named name. Okay, this also This has to be updated. This works, which rid of this. So now we have this namespace that I told you, this namespace file system. I don't think I explained exactly how it works, but at least now the code works. Tests. Fix. Good. Let me run the test and then look at the test. See what. I'm trying to remember. Did you? Yeah. Maybe in a video or something. I'm trying to remember your debug a problem, but I think you had tried to build before you test, but little reminder, you don't actually need to test it.
I was trying to do test, but it was giving me the same problems as build.
Yeah.
The version issues.
Oh yeah. Did you get that resolved? I forgot that.
Oh no, not yet. I was busy like with other stuff.
All right.
Yeah.
3. Kernel. Little test. All right, let's look at the test. This test namespace. So here's a file system. Okay, it's using fs test. No. fs test, which is fine. Made for tests. So here's a little file system. There's a file, there's a directory with a file in it, and a directory with a file in. We create a namespace. This file system has bind, and bind lets us, looks like AI gen. But basically, it lets us say, given this file system, we want to take this path in that file system and bind it to this path on the namespace file system. It's basically like attaching it to a point, but in a way that's not so declarative. You know, our mapfs kind of let us do that, but this is one that's interactive. In theory, we can unbind it and stuff like that. So this is a more of an interactive one, and namespace is also going mutable, so it will have to implement all of the mixture and remove. So anyway, namespace is an empty file system, and then we have this other file system, testfs. This file will be bound in our namespace as bound file. And bind has this mode, and this isn't necessarily the API that it will be, but basically in Plan 9, you can replace a binding. You can bind after or before. Basically, you can bind multiple things to the same file. And the file that will be used is the topmost one. So binding after will basically make sure that it's at the top, whereas binding before is gonna bottom of that stack. That's a very Plan 9 thing. No, most file systems, you can't have files with the same name. In Plan 9, you can. And part of that is to support this overlay concept. So anyway, the test is then going to read bound file on NS and make sure that it's content 1, and it is. We can also do this not just for files, but for directories. So here we're taking the root of testfs, so basically all of these, and we're putting it to bound directory. So on ns, so now in ns we can say bound directory and then go in there. So you kind of get the idea of what namespace is.
Mm-hmm.
It's in a way very similar to these other file systems, but the whole point is that it's empty and you can just bind stuff into it. This is what Plan 9, this is essential to the Plan 9 magic, because every process that runs in its own namespace. And a namespace is a view of possible file system. When you create a new process, the namespace that process gets, the file system that it gets, is a clone of the namespace of the parent process. So by default, if I'm, this shell program, this is bash or whatever, obviously when it reads the file system, it sees my actual system file system. If I were to start another program or even run bash from here, it would run in its own namespace, which by default would look exactly the same. But the cool thing is in Plan 9, you can then customize it. So you could either remove stuff. So maybe this process I'm creating, it shouldn't have the capability to create file systems. So we'll just remove that binding from its namespace. Or if you look, if you remember some of the Plan 9 material, like a lot of system devices are files or file systems. And so you can control access to them by adding or removing them to the namespace for a process. That's pretty neat because it then becomes a kind of a security model. Certain processes have access to things and others don't. And then you can do neat stuff like, make when I run this process, my file system looks like this remote system. And that when it actually does operations to the file system, it's actually doing those operations to the remote file system. So a namespace is really important for Plan 9. And so this is kind of a rough implement of that. Right now it's only implementing open. So we'll have to in time implement remove and make dir and all that stuff for it.
Potentially a good breakpoint.
Yeah. So we proc. So basically I'll say when we come back from break, we're gonna work on another file system, sort of the other main primitive of this kernel besides file systems or devices, which is processes. And so for now, it'll look pretty similar. It'll have a new where you can register types of processes. And then when you create them, it creates directories. And they'll have information about the process and the ability to control the process. But the main thing is that processes are how we create namespaces. So in order to use namespaces, we need to create processes. So I have a rough sketch of that. It's very similar to FSys, but we'll basically update that when we get back. And then we'll try it out and look into some cool stuff with content. So anyway, let's take a 5-minute break. Good spot. Be back
Okay,
at
10 or 11 after.
and yeah.
All right. Oops, yeah. Hello.
Welcome back.
Hi.
Back at.
I'm here.
Okay. Get back. So, in our sort of new kernel, project, we have a kind of a new top level directory called kernel. And this is where we're putting the stuff that's really specific to what we're doing with Wanix. You know, file system stuff, that's generic Go stuff. File system kit, that's for building file system again, but specific to this file system abstraction. This will eventually, as well as FuseKit, moved out of Wanix into basically a project called Toolkit that's basically a collection of general abilities. So really the first package other than main package command for Wanix is kernel, and we've got a couple of things in here. One is fsys, which we saw, it's this our file system device. Namespace, which we just saw, and then proc, which and okay, no, I put fsys over here because this one is sort of finished, whereas I actually started sketching out sort of wishful programming. What, without implementing union and map and stuff like that, what could it look like? How could we implement a file system? So this is a little out of date. But it's mostly going to be doing the same things. I guess one difference here is lines. Maybe that's fine. Process. These processes in Wanix are going to be abstract. It could be web worker. It could be a native system process. It could be a lot of stuff. Let's use pconc. Update. Whatever. The factory takes some arguments. It's probably a good idea. Obviously, there's a register. Oh, there's a constructor here that we could. And it's pretty much exactly the same so far. Good. This all points to maybe this whole concept of a file system that manages resources. Maybe we could abstract that into a utility that would make it even easier to build these kinds. But we'll wait. We'll make a couple more. Though this one, so instead of a control node for the file system, the proc file system has a self file, which is going to return the ID, the resource ID, process ID of the process that's reading this file, as a way to identify yourself. So if you then want to look up which process ID me, you'd find that out by reading /proc self. And so this is the whole reason why this context, this open context stuff was, because if we just have open, we have no idea who's calling open, you know, any way to associate different processes or different, callers. Whereas context is this, idea that's very specific to Go, where it is a type that has some common use cases. Like often it's used for timeouts. So you pass context into things that might take a while. You can create a context that has deadlines. So something can cancel if it takes too long. And context can do a couple of other things. It can be cancelable. So maybe it's a long-running process and you want to be able to cancel it. It's sort of like triggering a timeout, but whenever you call a cancel function. But the other thing a context can do is contain values. And so it becomes this like interesting way to pass more data into a function call than the arguments. As in theory, we could put anything in this context. And the point of that is that context is something that you pass through, sort of pass down the call stack. And so context is literally sort of the upstream context of the source of that call stack, right? So to me, that felt like the perfect place to store the process ID or the calling process, right? That sort of context to this call. So we'll finally get to use context for self, but we'll come back to that. New, this is all the same. That looks pretty good. And it gets a little different because it uses func file. And we're pretty much doing the same thing. So I'm just going to copy. Instead of resource, though, we have process. Doesn't have any of this. Let's actually all of this for now, and then we'll modify. Okay. Otherwise, this all works the same. Yeah. And then process. Now, did I say what? And for the most part, we're gonna punt on it because we're not actually gonna use this for making a process. Probably want a control node. That's where we would send kill or close or whatever to stop a process. Type is a good idea, so it can identify what type did we make. If you looked at Plan 9's version of this, and we'll eventually get there, all the file descriptors, you can get the environment that it has, what arguments it was called with, all of this stuff about the process, and some of which you could actually change, but we're gonna put a lot of that off. Really, the main thing that we want, though, is the namespace. So if every process gets its own namespace, we can expose that here so that we can see what's in the namespace. We could also modify the namespace. And of course, the running process is only going to see this namespace when it looks at its file system. But this is how we'll start playing spaces. And in theory, I'm thinking of even a type of process that's just empty, or maybe we'll call it NS, where the whole point of the process isn't to, manage some process or thread or whatever. The whole point of it is just to create a namespace for whatever reason. Maybe we have, we want to create a namespace to mount somewhere else. But this is that kind of Unix philosophy where if the namespace concept is tied to the design of processes, we can just use processes as a way to manage namespaces, as opposed to then having a separate resource to manage namespaces, where we'd have to create a namespace and then create a process and then use that namespace. So yeah, we'll do control, type, and base. We got control. We won't do anything in it though. We'll just log. There it is. Type. Then yes. Okay, well, for now, we'll just base in. I think we're always gonna. See a problem, Rohit? Missing something. It looks like I defined those in file system. I guess we can pull those out. I'm afraid to put them. Go ahead.
I was just thinking, do you have to include those? Where are these defined?
I mean, they were defined right there.
Yeah.
We could import them from file system where they were defined over here, but they're not really specific. I'm trying to find a new home. Like, I made them locally to this package because that's where I first needed them. But now that we're using them somewhere else, probably. I'm afraid to add them to kernel because if kernel ever has code that needs to include fsys or proc, it'll have an import cycle. In theory, we could add them to fskit, but they feel very specific to plan 9. Maybe we'll put them in we'll make a
We can make like a
plan 9 kind of. Yes. Auto. Okay, cool. That's pretty much everything. I guess this isn't too small, is it? Visible, readable.
Oh yes, it's readable.
Okay. So unlike file systems, we don't call mount the namespace. So do it at allocation, which means base. What? What is it? Func file. that means add field keys. It's somehow, oh, it's auto complete. Okay. Yeah, so right now it doesn't actually effectively do factory. It will create a namespace for this. So that's part of it. What else do we need to do? Let's try doing this self. We're going to go down this context rabbit hole. Context. I'm trying to, there's some design patterns. Emulate best practices. Basically, a context. We haven't used context. If we call value, we can give it a key. Key can be any type. You might think a string or something like that, but it's good practice that if you're putting a specific value in there, that you create an actual context key. That you actually create a custom type so that it has a unique sort of not the source for, pretty sure context key. Here. Context key. Doesn't I guess if this was GitHub. In theory, I think we could open this code. Oh, but technically. Let's pretend we're doing that. Just then we can. Okay. So they. Context key is a value for use with value. It's used as a pointer, so it fits interface. Oh, it's yeah, we. So anyway, this is kind of a fancy. Context key and then the whole point. Process. We're going to try storing the process in. focused. So the point of that was now we can do this is kind of how we would get this out. But then the return type for our context value is any. So it actually becomes common practice there to be a helper utility. What is helper? Getting specifically curious about the naming. Okay, user from context. So basically, they'll create a helper like this, something from context. You pass it a context, and then it will return a properly typed value, which most of the time it's just doing type assertion, whether or not it was in. Do something like a lot of infrastructure for basically storing a value in a context, but trying to think if we want to actually store a pointer to the process struct, or if we want to just store the A. I don't. And I guess with these helpers, take these in, but it's helpful to documentation to know what kind of stuff you. So this might all change, but oh, this is a bad idea. Properly. Usually you want the direction of dependency to go in outer package. Usually don't want the inner packages. Loose. Okay, so now we have a way out. I guess we'll just otherwise I guess it has an integer form. We'll return it as a Um, right. Use. What
Yes.
file? Field file. Oh, field file returns a
Yes.
file system, but a
Okay.
file system quickly become a obviously. Yeah, so this was implemented. Even though we call it file, it's implemented file system just because a lot of our helpers want. And we can pretty easily convert it to a file. This about invalid. Talking about. Problem with. Oh, we got another circular. Man, where put this? I guess because this is all specific to a process. Okay. So this is roughly what the implementation would look like. Look at the context, get the process out of it, and then ID itself. Now the harder part is creating this context. Because right now we don't have processes. We have, well, we sort of do. We have a process that we run here called serve, and basically represents any interaction via fuse. So because we're using fuse, we're not going to get the benefit of, we're using it on the file system here, we're not going to, basically the process ID will always be the same via fuse, almost as if fuse is. But you have to complete that process. You don't. I guess it's by reading. Could do that. Let's try that out. Now that we have proc, create a process type called NS. That's just an empty process. Purposes of creating a namespace. We don't actually use the. Now we could, in theory, create a an NS. We could just use our standard like read file. this. That's going to give us this is something we could wrap up helper later, but I guess if we just want to get the directory, is that what we want to do? I have this idea that if you can get a file for something like file, it give you access to struct probably just using ID. Yeah, we'll just instead of store that in a change our context. We might change it back. The background context is root empty context. I think that prints with a new line. That's a thing I need to figure out. I can. Now we need to somehow make it so that FuseKit uses that context for all its operations. So it's going to have to be pass it in. Yes, we will. create a node, lookup. So those are places we'll basically add a node. Here. And whenever we create new nodes, we can. All right. Oh, and then lastly, we actually need to call open with open. FS. I made a helper for. Oh, it's open. Well, now, probably this is it. Fuse has its own package called FS, so IOF else. Oh, it's different. Feels like such a normally context is the first argument. Is kind of the but if you already have a convention where something else is the first argument, which one wins? Yes, I ended up anyway, that could change. So open, that's the only place we open. We won't get a context if we call have version of that. But that's okay, because really the only times we'll use context in our file system is for a read-only file system. Like, that's going to tell us something about the context. All we have. CLI context. Oh, because we already have a so we need to call this. Okay. So now when we run serve, we're going to create a I guess we don't mount it. So maybe now we actually need to use the namespace. Works. Getting kind of self-recursive. Because we're creating a process in order to get a namespace that we're going to use to represent the namespace used by mount. Now we're talking about creating that namespace just so that we can actually put both of these file systems. Create our own here first, and so by s place. Nothing else. Check for errors. Yes, do it twice. Oh, it almost. Rock. Bess. Which means actually here we actually now have to. Wait, no. Okay. I think we have enough where we can get self to return some kind of number. 1. The process that it here. But this will prove that our context infrastructure works. It's possible that all these wrapping stuff that at some point, if something doesn't use open context, that it doesn't get passed into the next file system open. So let's now what do we have in? That's not what I wanted to see. Oh, because we're still mounting just defs. Okay, yeah, did you catch that, Rohit?
Yeah, I thought it.
We made a namespace so that we could have both.
Yeah.
And ultimately, we want it to be a. Okay. Dev proc. In proc, we should actually see 1, as we created a proc, quote unquote proc here. Where didn't we have self? Proc. Where's self? We've got new. Does new include NS?
And did it throw an error while creating?
Oh, I know what's happening. No. Huh. Oh, well, so, okay, I think. There's probably something that we need to do, but self is not a directory or a file system. It's really just file. So basically a field. This will do. File does not exist. Who? Where? Tell me more. Find fail. File does not exist. fix the source path. Source, that would be. I'm affecting its. Well, okay. No, this makes sense because we're returning that. If there's no context, it'll return does not. So this is probably the fact that the PID it's not going to be in the context yet because we haven't set it up. Maybe what we we do make this dynamic. I'll have to then we'll check the context, and then if is that sort of like with mount additional file. Hopefully this should get us past this. Okay, fine. Have self. Are we about time? About up?
Yes, we are.
Getting content. Well, we were pretty close. Something somewhere not passing the context. But I knew I wouldn't really be able to use it, so that off stream, basically this. Did do this even though kinda did this. So we're pretty close. Like once we get namespace stuff to work and the context stuff to work, we'll be able to implement the control command for bind and unbind because we now have a namespace that we could do that on. So hopefully by next stream, I guess week, we will have that and I can demonstrate it and go over it, and then we can kind of move on to the web stuff. Heather. Questions? Rohit, how was this?
It was kind of helpful. It was more of like a structuring felt like today.
Yeah.
Like trying to make it more
Move stuff
structured and
around
move
and
stuff
rename
around and
things.
organizing basically.
Yeah.
So
But
that
you know,
was
that's kind of a at least from because I create a lot of APIs and create abstractions, there's a lot of trying stuff. I move stuff around. I feel like there is a lot of that in programming, but not as much. But it does help
I mean,
us.
that is good.
Yeah, I mean, it helps us kind of better understand the type system and, why does this work and this.
Yeah.
But yeah, I felt it was nice that we were able to get to something that does something, in a way. We created a file system.
Oh yeah, definitely, yeah.
Right. So
I'm kind of excited to see how we make it work on the web.
yeah.
So that's where I'm like more excited to see. Like I want to see how do you connect it with another PC system and
Yeah.
like basically work on the web basically. So
Well,
let's
it
see
might
how
be a
that
little
goes.
different than you're expecting, but yeah, we'll find out.
Yeah.
Hopefully next week, and then I guess before we go, I wanted to say I'm excited for our stream tomorrow with working on the blog system with Tara, because the static site generator, because we had some breakthroughs with JSX, and since the last stream there's there with Tara, but I'm
nice.
excited. Site generator that we're gonna call
That's
TerraGen.
Well, cool.
All right, thanks everybody.
Thanks again for like showing us.
Yeah, I'm hoping you're getting a lot out of it.
Oh yeah, definitely like learning a lot.
Cool. And everybody else, hope you're all learning a lot too. Are you learning? You're following along, right?
Mostly following.
This is like deeper abstraction.
I mean, at least like some syntax stuff and some
Yeah.
organizing principles and
Osmosis.
things like that. Yeah.
All right.
All right.
Well, that's it.
Bye.
Everybody later.
Bye.